Hi, welcome back to our lecture. Right, overall, what we have done in the previous chapter 2, chapter 3, chapter 4 are mainly about the differential calculus. Right, chapter 2 we had seen an idea of how to do the limits. A related topic to the later was how we find the horizontal asymptotes, so-called. Right, then we use everything from our pre-cal and the cal, right, pre-calculus and this part, right, the increasing, decreasing intervals and so on, right, the concavities, to graph the actual graph of our functions. Right, and before, right, if you still remember the beginning chapter, we have seen that, well, the difference of quotient, that's y2 minus y1 of x2 minus x1, the same thing, right? Or we call that delta y over delta x. What we, in the view of pre-cal, right, we see the difference of quotient. That is x of plus h minus f of x over h, which are same thing. When the difference of x approaches to 0, in other words, the h here approaches to 0, we don't have no more the dy over dx. I mean delta y over delta x, but we have is dy over dx as a derivative of y, right? dy dx equal y prime. And moreover, right, besides that, the delta y is over delta x is the slope, right? It will be found by multiplying slope times our delta x. And in the view of short one, for dx to be very, very little, but for a certain fixed value, let's say, that is y prime at the derivative times dx. Right, so for a function, right, for the one variate function, the dy dx is a separatable notation that we are able to, since well, delta y over delta x is the slope, is also an separatable notation, right, since they are equal, right, the slope basically, then dy over dx is also a separatable notation. Right, that is only true for the one variate function. Maybe we have later for function have 2 variables, 3 variables, that may not holds. Right, that is the certain thing could be called differential equation. I believe in our class somewhere we have seen the word of differential equation already, which this part could be called ordinary differential equation, which doesn't matter how much order we have, maybe second derivative, maybe third derivative we have involving the function, but we still have derivative, right, of a function with a single variable x, right? That is ordinary differential equation, right? But things will change for multivariate, right? So be careful when if you go to multivariate, you will be super careful that the notation may not be able to separate. It only can be separate the dx and dy and the dx is actually a division, right? Only in the case of single variate function. So that is before our next chapter, what we are something extra to clarify, right? And next chapter is just touch a little bit of what it is. Right, chapter 5. Is the integration. 5.1 is about antiderivative. Antiderivatives and indefinite integration. Right, so what is antiderivative? Right, we know what derivative is, and for the phrase in front of it, that's anti, right, which counts like maybe something like opposite, right? So we see about the definition or the example of antiderivative. So consider the function f of x equals 3x squared. And whatever we have given the function f of x, the derivative of capital F of x is 3x squared, which is the lower f of x. Right? That's what we can see. And also the g of x, the capital G, is x to the third plus 2. Right, so also the g of x, that is x to the third plus 2, has also a derivative of f of x. Right, in this case, the function big F and big G are two antiderivatives of f. Right, since the big F has a derivative of f, the big G has a derivative of small f also, then the functions big F and big G are called antiderivatives of f, which means you differentiate f and g, you'll get the f. That's called f or g. Those are the antiderivatives of our f, right, of our function f. So that is the observation we got. Right, then the true definition. Right, the function big F is an antiderivative of small f on an interval I when f prime of x equal f of x for every x on the interval I. Right, also the g is an antiderivative of f. Well, IFF stands for if and only if. Gx equals f of x plus c. Right, that we have seen the example before, right? Any constant of x to the third, let's call that k of x. Then any constant attached to x to the third will have derivative of 3x squared. Which is our f of x in the previous example. Right, so the k of x, the c could be any constant, arbitrary constant, that attached to it, doesn't matter what it is, will always have the derivative of 3x squared. Now in the view of x to the third, right, just differing constant, right, for whichever this graph looks terrible. Right, that looks a little better. For whichever constant it is, right? But its derivative is always 3x squared. That is all increasing function, but it's concave down and concave up in the view of the first derivative, what it tells us, right? The derivative is positive always, that shows the original function is always increasing, right? Is decrease and increase for the derivative, that means the original function is concave up, concave down, then concave up, right? That's what the derivative tells us. Right, and the only differing constant, that g will be also the antiderivative of f. So in view of notation, for the f of x to be dy over dx, then what we can do is as mentioned, separate our dy and the dx. To multiply dx on both sides, we get that notation. And the integration symbol we apply to both sides. It is like a extended S, right? Or some F, but no, not a horizontal line. right? Something like that. That is the integration symbol. So the integral of dy, right? Integral of y in respect to our constant y, our variable y, that is invisible 1 over there. And we have a integration of our lowercase x, fx, respect to our variable x, right? So the d something is the respect variable, right? It could be respect to y, it could be respect to x, like what the derivative, same thing, derivative of y respects to the variable x. I will take the variable x to the derivative. Here is just taking the integral respect to the variable of y. And when we apply on both sides, integral of dy, that will give us the y, is integral of f of x dx. By definition, we see is the capital F of x. And the antiderivative is not a unique answer. Right? It will be a group answer as we see. It shares the same derivative of a group of function that differs with constant. Right? That differs with constant that we see in the idea. So when we apply the properties of antiderivative, we have to plus a constant at the end. That's an arbitrary constant. So, since the derivative is just an antiderivative, right, what we will do is they will still have some basic integration rule, right? We will see. The first one is, well, antiderivative of a 0 is a constant. Antiderivative of any arbitrary constant k, that is kx plus c. I just attach the variable to it. Now why it is true is because the derivative of kx is equals to k. Right, so when the antiderivative of a constant, that will be just attached the variable on its side. Right, and the third property we'll see is x to the n. That rule is we have a rational that x will have power adding 1. And of course plus constant. In that case is for derivative of x to the n is equal n times x to the n minus 1. Right, so given that, you could use this one, right, as what it is, and you could try to verify this formula, right, this one, for the power rule. Use this property of the derivative, right, try that. And one additional condition, right, is that n cannot be -1. If n is -1, we get 1 over x. That denominator will be 0, x to the 0 over 0. That is simply undefined for the function to be exist. Right? So n cannot be -1. If we have x to the -1, that's 1 over x. Or maybe that record to something else when it comes out 1 over x. Right? But well, we just use up to this thing, which is still the linear combination of polynomials we will see. Right, same as derivative, this will be also separable. So any property of the linear combinations, it will be applied for the integration as well. Right, so that is the basic integration rule. So try to take the antiderivative of 1 over x to the third of square root of just dx right. Well, similar as derivative, right? We do integration. Integrating it, we need to apply power rule that, well, the power will be flipped and make it to x to the certain power. As long as it's not -1, what we can do is apply the power rule, x to the original power plus 1 over the new power. Once the integration sign, or once we use the power rule, the integration symbol and dx will be cancelled out. Since we apply it to the variable of x, then we put the power rule of x, right? If not, then not that like. But one thing is, if we apply the rules, right, for the antiderivative, right after we need to put the plus c, right? Right after we need to put plus c. Then what we have is simply, after we simplify with what we have, right? -2 x to the -2, which x to the -2 is 1 over x squared. And we have -2 on the bottom, so -1 over 2x squared right, -1/2 -1 over 2x squared, basically, right, plus c. That is the antiderivative of this 1 over x to the third. Then the radical x, we have it x to the 1/2 power, first of all. Then apply the power rule of integral. X to the 1/2 plus 1 over 1/2 plus 1. And don't forget, of course, you are new to that, so it's very easy to forget the plus c. Right, so once you don't write the integration sign, you have to plus c. Right, it's like doing the integration. This thing is called indefinite integral in the name of section, that we do not have any like value evaluated, right? It's just the original function, like the extended on piece. So once the integration symbol cancelled out in the indefinite integral, we have to plus c. So we get x to the 3 over 2 over 3 over 2 plus c. That we could flip the 2/3. X to the 3 over 2 if you want to keep, or if you want to write it as radicals, that's cube of radical x. Right, that's apply the power rule. Right, again, power rule is just power adding 1 over the new power we have. Right, the last one, well, that's just invisible 1 there. Right, for the term to exist, the middle has to be 1. If you get confused, you could put it. the integration of any constant that's just constant times x times the variable basically, which is x plus c. Right, so it's simply asking, well, what function has a derivative of 1? Well, we get x plus c has a derivative of 1, right? So if you want to, you could double check your work, right? To check the derivative of x plus c, that is 1 plus 0 is 1. Right, the derivative of 2/3 times x to the 3/2, which is 2/3 times 3/2 times x to the 1/2, that is radical x. Right, the derivative applied to that, of course, plus c will give you 0. Right, we'll back to the function inside the derivative symbol. That is the way to check our solution, right, to see if it's appropriate. Then for something else, integral of x plus 2 of 3x squared minus 6x to the 3rd plus x. Alright, similar doing. Well, we have x plus 2 have x to the 1st power, so that, right, separately, that's x to the 1 plus 1 over 1 plus 1. And 2 taking the antiderivative, that's 2x. And then after every term we applied, plus c. Right, so we get x squared over 2 plus 2x plus c. Right. And the next one, the coefficient, whatever it is, that's x to the 2 plus 1 over 2 plus 1, x to the 3 plus 1 over 3 plus 1, x to the 1 plus 1 over 1 plus 1. I'll just be clear of what that power is, and then we just apply the power rule for the integration, right? It will be opposite as what we do for the derivative. What we do for the integration is take the power plus 1 over the new power we had. Right, so we get 3 times x to the 3rd over 3, 6 times x to the 4 over 4, x squared over 2, we get x to the 3rd, minus 3/2 x to the 4th, plus x to the 2nd over 2, or if you want to be consistent of what it is, you could put 1/2 x squared and plus c. Right, or if you want to keep the nicer order, you could keep the power in descending order. That's all acceptable. Right, this part is good enough. Right, so we do not want to see the simplifiable coefficient of the x, but this format, even not in the descending order, that is also fine. So that is also called indefinite integral. It's just the antiderivative of functions we're looking for. And the next question, we have x plus 1 over radical x. Right. The only thing we have for here, right, is the power rule. So we don't have nothing else. So what we could do is separate the function and simplifying it, right? And by dividing it. That's what we see how we deal with this type of thing to differentiate. Right? Similarly, we had seen that before. Then apply the power rule. That is 1/2 plus 1 as the power. The other term is negative 1/2 plus 1 as the power. Plus a new constant. Then to simplify it, we get x to the 3/2 over 3/2. And that is x to the 1/2 over 1/2. Now we get 2/3 x to the 3/2, or square root of x to the 3rd power if you want to write that, and twice the square root of x. So that's the indefinite integral and mainly the power rule, right, how we do that. Well, since our course, again, we mentioned is mainly about the differential calculus, then the integration part will just touch a little bit of it. Right, the next part is 5.4, the fundamental theorem of calculus. Which the definition, definite integral, which section 5.1 we see was the 5 ones we have seen was the indefinite integral, and the definite integration is the notation we have that integration symbol, could be more better, of f of x. The value a and b is like the subscript and superscript from a to b of f of x. That is a graph of f on the variable from a to b. If f of x is continuous and positive, then integration from a to b of f of x dx represents the area under the curve and bounded by x equals a, x equal b, and x-axis. Right, so if f is positive and continuous, this area, which is a curve under the curve f, right, is the area under the curve f, bounded by the x-axis, the vertical line a, and the vertical line x equal b, is the meaning or geometric meaning of the integration. How we calculate it is when f of x is the antiderivative of f, the integral a to b f of x dx is antiderivative of f of x evaluated from a to b. Right, from a to b, always we consider from left to right. From right to left, that's will be another theory to cover, another property to cover, but always from the left to right. That is the antiderivative of f of x goes from a to b. That could be evaluated as f of b minus f of a. Okay, that's how we evaluate this antiderivative. And of course, if there are linear combinations, then what we can do is evaluate each part or each piece separately. Altogether is fine, but each piece is also fine. Right, so that's what this thing is. And then let's see some example, right? For the definite integral, what do we do? The definite integral of x to the third minus 3 for x from 1 to 2. Right, what we do is it is saying evaluate the antiderivative, that's x to the 4th over 4. Right, for the entirely function from 1 to 2. That's 1/4 x to the 4, 3x. What we could do is from 1 to 2. We could separate that there are linear combinations of function that we can evaluate the 1 to 2 for each of the variable. What it means is instead of doing the entire thing like 1/4 times 2 to the 4th minus 3 times 2 minus 1/4 times 1 to the 4th minus 3 times 1. That will be very tricky to do, right? If we evaluate the top and bottom for each inside the parentheses, right, we'll get maybe fractions or so. A little trickier. But if we do that, as long as we get linear combination, what we could do is 1/4 times 2 to the 4th minus 1 to the 4. 3 times 2 minus 1 of the evaluates of each variable. And then we get 1/4 times 2 to the 4, 16 minus 1 is 15 minus 3. And that's 15 over 4 minus 3, which 3 is 12 over 4. 15 over 4 is 3 and 3/4. So that thing when we subtract is just 3/4. Now if we go over here, that may be causing a little bit more trouble of the numbers. Right? We have the calculation in the middle and negative sign usually is causing more serious trouble. So when we have linear combination, of course personally, if I do this type of question, I will evaluate the integral one by one. And that will be, I feel, a little easier at least. I also recommend it. Then the next one, integration of 2 radical x. Well, the 2 radical x, that is from 1 to 4, that's 2x to the half. And we applied the integral rule already, so we don't have to do that 2 times. Well, x to the 1/2 plus 1 over 1/2 plus 1. Evaluate it from 1 to 4. So realize that, well, we have definite integration over there, we do not need to plus c. Even though from a to b f of x plus c, right, for the a to b, even though we do plus c, that c will be cancelled out at the end. we get FB plus C minus FA plus C. Then the C's will be cancelled out in the afterwards. That's still f of B minus f of A. So that we didn't mention, but you could consider over here. We don't need an additional constant since everything will be cancelled out at the end. But anyhow, right? So that's 2 times x to the 3/2 over 3/2. Which is 2 times 2/3, right? That's 4 over 3 times radical x to the 3rd power, taking value from 1 to 4. Right? That's a single term. So we have to apply 4/3 times radical 4 to the 3rds minus radical 1 to the 3rds. Right? Radical 4 is 2 to the 3rds is 8. 1 to the 3rd is simply just 1. That's 7. 4 times 7 is 28 over 3. Right, that is this function. Then for the next one, which will be a little trickier.